Okay, continuing on here with our practice exam. On the fourth page here, we have some problems on solid state structure. So looking at the first part of question number 5 here, we want to look at how many atoms or ions, depending on which part we're looking at, are there in a unit cell that matches the following description? For full credit, show, justify your calculations. So I'm going to draw them. I might ask you to draw a cube or something like that on a test, usually as an extra credit problem or something like that. But I think it certainly is a helpful practice to draw the cube. Physically drawing it will help you remember and understand all the positions of where the atoms are, and that could help you kind of recognize relationships within the cube too. So I think it's good practice to draw it, right? I'm not necessarily going to test your art skills here in this class, but I think there's a link between what you do with your hands and what your brain understands. So certainly if you go on in chemistry and you get into organic chemistry, it's very helpful to draw your three-dimensional structures. So anyway, moving on here, part A, a primitive cubic or a simple cubic unit cell. Primitive cubic, simple cubic are the same thing. The terminology is used interchangeably. So this is a cube, and it's simple because the atoms involved in the structure only exist on the corners of the cube. So there's our cube, right? And our atoms would exist just on the corners of the cube. Now, we want to calculate how many atoms, right, or ions are in the unit cell. Atoms in this case, if it's just a neutral molecule. We've got an atom on each corner. So atoms are on the corners, and there's 8 of them. What we really need to think about there, though, is how much of that atom is in the unit cell we're describing compared to how much of it is in, right, there's another unit cell above this cube, another unit cell over here to the left of this cube, another unit cell in the front, right, diagonal, right, and above in the front, and above in the diagonal, above to the left. Right? When an atom is on the corner of a cube, only 1/8 of it is in the cube we're talking about. The other 7/8 are in adjoining cubes. So to calculate how many atoms are in this unit cell, we take the number of atoms on the corners, multiply by how much that atom is in the unit cell, which is 1/8, and that would be 1 atom. There's only 1 atom in a primitive or simple cubic unit cell. Okay. Moving on to part B, body-centered cubic. Very similar here. We've got a cube again. Right? There are certainly other types of crystal structures, but they all get more complicated because they don't have all nice 90-degree angles and the same distance on each side. Body-centered cubic still has atoms on the corners. So we still have those 8 atoms on the corners, and that will be part of the calculation. 8 again times 1/8, so we have 1 atom in there from the atoms that are located on the corners. But body-centered means there's another atom right there in the center of the cube, or in the body of the cube. Now if an atom is in the body, it's completely in the unit cell. So there's 1 there, right? All of it's in, right? So I'm multiplying by 1 to kind of keep it consistent with the way we're showing the calculation there. I'm hoping you guys are pretty solid with being able to multiply by 1 and do that mathematically, right? There's 1 atom that's completely in the body, and that means there's a total of 2 atoms in a body-centered cubic unit cell. Okay. Now, getting trickier to draw as we go down. Part C here is face-centered. So again, we've got a cube, and there are atoms on the corners here as well. So on the corners, and again, there's 8 of those, so we still have corners. 8 times 1/8. There's 1 atom represented by what's on the corners. Now, a cube has 6 faces, though, and this is where it gets a little harder to draw. So let me start with the ones that are easier to draw. And then I'm right there in the middle of the top face, right? Almost like the 5 on the side of a die where a 5 is, one on this side, right? And there would be one on the left side as well, and one on the bottom, right? And then harder to draw here with all the things going on is there's one on the front face and one on the back face. Right? So whether you can draw those and see all the differences or not is not necessary, because if you just think about how many faces are on a cube, there's 6, right? And looking at the one on the top here, that atom is right in the middle of that face of the cube. Half of it's in the cube we're looking at, the other half of it would be in, right, this next cube up above as we move out into the three-dimensional structure. So 6 faces, each face, half of that atom on a face is in the cube we're looking at. That adds another 3 atoms for a total of 4 atoms in each unit cell if our structure is face-centered cubic. Okay. Excuse me. Moving on to part D. Now we're talking about an ionic compound or ionic material. Primitive cubic anion lattice. So the anions are arranged in the similar fashion to what we saw in part A there, the primitive or simple cubic lattice. And then there's a cation occupying the cubic hole. So when we describe a cubic hole, that means that atom is surrounded by a cube of whatever the opposite ion is. So let me try to make this one a little bigger. I still want to fit it in the space there, but I want a little more space to draw. Even more so in the bottom though. So here's our anions. Our anions are here still on the corners. Right, and then there's the back corner there. Right, so as far as anions, it's just like part A. There's 8, they're on the corners, so that's 1/8. There's 1 anion in the unit cell. Now I'll use my blue pen here for the cation. But I'll hash it as well so that you can tell by the hashing as well as by the color. If the cation is right there in the center of the unit cell, then that's kind of like a body atom. So cation, there's 1 in the body, so let me write that in there too. Anions are on the corners here. The cation is in the body. 1 times 1, there is 1 cation in this unit cell, right? And you can, because of the atoms being on the corners, you can see the cube, right? This cation is surrounded by a cube of where the anions are. So it's considered a cubic hole. The cation is in a hole within a cube. Okay. E. Trickiest one to draw for sure. An ionic material with a face-centered cubic lattice, just like C. Cations occupying the octahedral holes, right? And again, we want to calculate. So let me do my best here at drawing this one. Giving myself more space here, nicely down at the bottom of the page where there's a little more space. Okay, so there's my cube. Now, anions are face-centered cubic, so I've got an anion on each corner. But I've also got an anion on each face. So one up here on the top, one on the right, one on the bottom, one on the left. Now I left a little more space to put the one in the back there, right? And then there's one in the front here too, right in the middle of the front. So as far as anions, this would be much like part C. The corners are 8 times 1/8 equals 1. And then the faces, 6 times 1/2 is 3, for a total of 4 anions here. Now, the cations are in the octahedral holes. Now, the octahedral hole that is easiest to see would be a cation that is right here in the body, in the center of the unit cell, because one of the anions is above it, one is below it, one is to the left, one is to the right, one is behind, one is in front. So that cation is surrounded by an octahedral shape of 6 of the anions. Okay, so as far as cations go, right, 1 is right in the middle in the body. 1 times 1. 1 cation. The other octahedral holes are along the edges. So let me try to hash those instead of filling them all the way in. I think that shows up a little better. in terms of recognizing that they're different. So right on that side, there's 4 edges on each face, although some of them are on multiple faces. So there would be there, 4 along the top. Right, there's 4 along these edges, along the sides, and then there'd be another 4 along the bottom, right in between all of those. Okay. Each of those is an octahedral hole. Now you don't see the whole octahedral because some of the atoms that make up the octahedral are in other unit cells. This one on the edge here, you can see one above, one below, right? One behind and one to the left. The one in front would be in the next unit cell in front of this one. The one to the right would be in the next unit cell to the right. But in addition to that one on the body, there are atoms that are on the edges, or cations here, not necessarily atoms. 12 edges. Each edge is shared by 4 unit cells, so times 1/4, that adds another 3. There's a total of 4 cations in that compound as well. Right, now this is it's kind of commonly referred to as the sodium chloride structure. Right, if the chlorides are in a face-centered cubic arrangement, these sodiums would end up on the edges and in the center there. Okay, we'll stop there. We'll pick up the last page of the sample test in the last video.